Every second of your conscious experience arrives a billion seconds late. By the time you look at anything, the result has already been decided, recorded, and distributed to 100 million independent witnesses. You are not observing, you are reading. You were told the opposite. Every physics classroom, every popular science video, every TED talk about quantum mechanics delivered the same story, that the observer is what makes reality happen, that consciousness collapses the wave function, that your mind shapes the physical world into existence. But in 1981, a physicist working out of Los Alamos National Laboratory published a paper that broke that story apart. And in 2025, a team in China confirmed it with superconducting circuits cooled to near absolute zero. The environment decides what is real. It does this at timescales that make human perception look glacial, and it has been doing it for 13.8 billion years without consulting anyone. Tonight, I want to walk you through what is actually happening when you think you are observing reality. From a buried 1970 paper whose author was punished for being correct, to the theorem that proves quantum states cannot be copied, to a single grain of dust recording its position 100 million times per microsecond, to a 2025 experiment that confirmed the entire framework, to the implication at the bottom of all of it, that the people who understand it would rather not say out loud. Get comfortable. This one runs long, and it runs deep. If you are not subscribed, now is the time. And if you want wider and stranger explorations across physics and the architecture of reality, the Patreon goes places a single video cannot reach. Stay for this one, because by the end, the question will not be what you know about quantum mechanics. It will be what quantum mechanics knows about you. Let's walk through it. There is a number that should not exist in physics. It appeared in 2004, buried in a paper published in Physical Review Letters by 3 researchers working out of Los Alamos National Laboratory. The paper was not classified, it was not hidden, it was peer-reviewed, openly published, and freely available to anyone who wanted to read it. And almost nobody did. The number describes something so specific and so mundane that you would think it could not possibly threaten your understanding of reality. It describes how many times the position of a single dust grain, 1 micrometer across, sitting in ordinary sunlight, is recorded by the photons that scatter off it in a single microsecond. 100 million, not over a year, not over an hour. In 1 microsecond, 1/1,000,000th of a second, the position of a single speck of dust is independently copied into the surrounding environment. 100 million times. 100 million redundant, independent records of where that grain is, encoded in photons that scatter outward in every direction, available to any system, any detector, any pair of eyes that happens to intercept them. And nobody told you about this. Nobody mentioned that the air around you right now is performing this operation on every object in your field of vision, continuously, relentlessly, at a rate that makes the entire concept of you observing reality feel like a joke you are not in on. That number is the reason you can see, not in the biological sense, not because of rods and cones and optic nerves. You can see because reality has already been decided before a single photon enters your eye. The environment, the ocean of particles and fields surrounding every object in the universe has already voted. It has already selected which properties of the object are allowed to be real. It has already recorded the result and distributed copies to every available witness. By the time you look at something, you are not collapsing a wave function. You are not choosing an outcome. You are not doing anything that the physics actually requires. You are reading. You are picking up a newspaper that was printed and distributed to 100 million subscribers before you woke up this morning. And the fact that you are told for nearly a century that the act of observation is what creates reality, that the conscious mind plays some special role in the machinery of quantum mechanics, is not a simplification. It is not a pedagogical shortcut. It is the single most misleading claim in the history of modern physics. And the man who proved it, a Polish-born physicist named Wojciech Zurek, has been publishing the evidence since 1981. The question is why you're only hearing about it now. That question has an answer, and the answer is not a conspiracy. It is something worse. It is the story of how physics decided, collectively and deliberately, that certain questions about the nature of reality were not worth asking, that the measurement problem, the single deepest unsolved question at the foundation of quantum mechanics, was not a real problem, but a philosophical distraction, that anyone who spent their career on it was engaged in something between self-indulgence and career suicide. And it is the story of what happened when someone ignored that consensus and followed the evidence anyway, all the way to a conclusion so disturbing that even the people who accept it would rather not say it out loud. The conclusion is this: you are not the observer. You never were. The universe does not need you to look at it in order to become real. It has been handling that on its own, with breathtaking efficiency, since long before the first nervous system evolved. And the mechanism by which it does this, once you understand it, does not just change physics, it changes what it means to be you. This is not a fringe idea. This is not a thought experiment. This is published, verified, experimentally confirmed physics with a name. It is called Quantum Darwinism. And the reason that name should unsettle you is that it means exactly what it sounds like. Reality is the product of natural selection, not the biological kind. Something older, something more fundamental, something that has been running since the first particle interacted with the first environment billions of years before the first living cell divided. The classical world you live in, the solid objects, the definite positions, the colors and textures and temperatures, none of it was inevitable. All of it is what survived. But before I tell you what that means, I need to take you back to the problem it solves, because the measurement problem is not some abstract puzzle that physicists argue about over wine at conferences. It is the crack in the foundation of the most successful theory humans have ever built. And the fact that it was ignored for 60 years is itself one of the most consequential acts of intellectual avoidance in the history of science. Here is the problem, stated as cleanly as I can manage. Quantum mechanics describes the behavior of every particle, every field, every interaction in the universe. It does so with an equation, the Schrödinger equation, that is perfectly deterministic. Given the state of a quantum system at one time, the equation tells you the state at any other time with absolute certainty. There is no randomness in the equation. There is no ambiguity. There is no moment where the math throws up its hands and says, I do not know. The evolution is smooth, continuous, and unique. But the equation says something deeply strange about the world. It says that quantum systems exist in superpositions in multiple states simultaneously, until something happens that forces them to pick one. An electron does not have a definite position. It has a cloud of possible positions, each with a certain amplitude, and the electron is in all of them at once. A photon, going through a beam splitter, does not take one path or the other. It takes both paths at once. A radioactive atom has not decayed or not decayed. It has done both simultaneously, in a superposition that is as real and well-defined as any other physical state. And here is where the problem bites. Because you have never, not once in your life, seen a superposition. You have never seen an object in two places at once. You have never seen a cat that is simultaneously alive and dead. You have never experienced the world the way the Schrödinger equation says it should be. The world you experience has definite properties, definite positions, definite states. The world the equation describes does not. The standard response to this, the response that was codified in Copenhagen in the late 1920s by Niels Bohr and Werner Heisenberg and their colleagues, is to draw a line. On one side of the line, the quantum world, particles are in superpositions, and the Schrödinger equation rules. On the other side, the classical world, objects have definite properties, and your experience of a solid, single-valued reality is correct. When a quantum system crosses the line, when it is measured, the superposition collapses into a single, definite outcome, randomly selected according to a probability rule proposed by Max Born in 1926. The Born rule says the probability of each outcome is the square of the quantum amplitude for that outcome. It has been confirmed to extraordinary precision. Every prediction quantum mechanics has ever made relies on it. But this response has a problem that is so fundamental, it threatens the entire structure. What counts as a measurement? Where is the line? The equations do not say. There is nothing in the Schrödinger equation that specifies when a measurement occurs. There is nothing that defines the boundary between quantum and classical. The line is not derived from the theory. It is inserted by hand. It is a fudge. And for nearly a century, the fudge worked well enough that most physicists decided it was not worth worrying about. Schrödinger himself saw the absurdity of this. His famous thought experiment with the cat was not a proposal that cats can be simultaneously alive and dead. It was an attack on the idea. He was demonstrating that if you take the quantum formalism seriously, if you refuse to draw an arbitrary line between quantum and classical, then the superposition of the radioactive atom gets amplified through the mechanism in the box until the cat itself is in a superposition, alive and dead simultaneously. Schrödinger was not fascinated by this. He was horrified by it. He was saying, look at what your theory implies. And the response from the Copenhagen camp was, effectively, do not look. Draw the line somewhere before the cat. Invoke the measurement postulate and move on. That was 1935. And for the next 35 years, with a handful of exceptions, that is exactly what physics did. Drew the line, invoked the postulate, and moved on. Shut up and calculate. And the exceptions were punished. In 1952, David Bohm, a brilliant American physicist who had already done foundational work in plasma physics and quantum theory, published 2 papers proposing a deterministic alternative to Copenhagen. In Bohm's theory, particles have definite positions at all times, guided by a wave that is as real as the particles themselves. The wave function does not collapse, it guides, and the randomness of quantum measurement is not fundamental. It is the result of our ignorance about the initial conditions. The same way a coin flip is random, not because coins are inherently unpredictable, but because you do not know the exact force and angle. Bohm's theory reproduced every prediction of standard quantum mechanics exactly. It was mathematically equivalent. It was internally consistent, and it was destroyed. Robert Oppenheimer, the director of the Institute for Advanced Study, told Bohm's colleagues not to work with him. The physics establishment did not engage with the theory on its merits. It dismissed it as ideological, as unnecessary, as the kind of thing that serious physicists did not waste time on. Bohm had already been called before the House Un-American Activities Committee for his political associations. He had lost his position at Princeton. He would eventually leave the United States entirely, spending the rest of his career in Brazil, Israel, and England. And his theory, which turned out to be a perfectly valid interpretation of quantum mechanics, was placed in a drawer. The drawer was locked, not for a year, not for a decade, for 60 years. Hugh Everett met a similar fate, and his story cuts even deeper because of who his advisor was. Everett was a graduate student at Princeton in the 1950s, working under John Archibald Wheeler. His doctoral thesis, completed in 1957, proposed something radical. Instead of invoking collapse, Everett suggested that the wave function never collapses. Every possible outcome of every quantum measurement is realized. The universe splits, not into separate physical spaces, but into separate branches of a single universal wave function, each branch containing a version of the observer who sees a definite result. The many worlds interpretation. Wheeler believed in Everett's work. He supported it. He helped get it published. But he also knew the political terrain of physics, and he urged Everett to tone down the language to avoid direct confrontation with Bohr and the Copenhagen establishment. Everett went to Copenhagen. He met Bohr. The meeting was, by all accounts, a disaster. Bohr did not engage with the substance. He dismissed the idea. And Everett, disgusted by the reception, left physics entirely. He went into military operations research. He became wealthy. He became an alcoholic. He died of a heart attack in 1982 at the age of 51. His daughter, Elizabeth Everett, who suffered from severe mental illness, took her own life in 1996. In her suicide note, she wrote that she was going to join her father in a parallel universe. The many worlds interpretation had consumed the family that created it. This is the pattern. Bohm, Everett, Zurek, Bell. John Stuart Bell, the Irish physicist who proved in 1964 that no theory of local hidden variables can reproduce the predictions of quantum mechanics. The man who demonstrated that the universe is either non-local or non-real or both, spent the first 15 years after his theorem working at CERN on accelerator physics because foundational work was not considered legitimate. John Clauser, who performed the first experimental test of Bell's theorem in 1972, was told by his thesis committee that the work was unlikely to lead to a career. He was right, and he struggled professionally for years because of it. The pattern is not conspiracy. It is worse than conspiracy. It is the natural behavior of a social system that has decided certain questions are settled and enforces that decision through professional incentives, grant committees, hiring decisions, and the slow suffocation of indifference. The questions were not settled. The measurement problem was not solved. The Copenhagen interpretation was not a solution, it was a refusal to solve. And the cost of that refusal was not just intellectual, it was personal. It fell on specific human beings who had the temerity to take their own theory seriously. And here is what makes this suppression different from other cases of scientific conservatism. In most cases, when the establishment resists a new idea, the resistance eventually collapses under the weight of experimental evidence. The evidence forces the issue. But with the measurement problem, the experimental evidence was not the bottleneck. The evidence was there from the beginning. Quantum mechanics itself was the evidence. The equation said superpositions are real. The equation said measurement is undefined. The equation said the boundary between quantum and classical is not in the theory. All of this was known by 1935. By 1970, Zurek had shown that the environment could explain the appearance of collapse without invoking a measurement postulate. The physics was available. What was missing was not evidence. What was missing was permission. permission to ask the question, permission to take the answer seriously, permission to follow the math where it led, even when it led somewhere uncomfortable. That permission came from one person, and he gave it not because he had more courage than his colleagues, though he did, but because he had spent 40 years doing the hardest physics in the world and had earned the right to ask any question he wanted. His name was John Archibald Wheeler, the first person who refused to move on, who looked at the equations and took them seriously, who followed the math where it led without inserting a measurement postulate or drawing an arbitrary boundary, was a quiet, methodical German nuclear physicist named Heinz-Dieter. And what happened to him is the founding injustice of this entire story. In 1970, Zurek published a paper titled On the Interpretation of Measurement in Quantum Theory in the journal Foundations of Physics. The paper is only 12 pages long. It contains no exotic mathematics. It does not invoke new particles or new fields or new postulates. What it does is something far more radical. It takes the Schrödinger equation at face value and asks what happens when a quantum system interacts with a large environment. The answer, which Zurek worked out with rigorous care, is that the environment does something specific to the quantum system. When a particle in a superposition of two states interacts with the surrounding air molecules, or photons, or thermal fluctuations, each state of the particle becomes entangled with a different state of the environment. The superposition does not collapse. It expands. The particle superposition gets absorbed into a much larger superposition that now includes both the particle and the environment. And here is the crucial part. The interference terms, the mathematical signatures that tell you the particle is in a superposition rather than simply in one state or the other. Those terms are now encoded in correlations between the particle and an enormous number of environmental particles. And to detect those interference terms, to verify that the superposition still exists, you would need to perform a measurement on the particle and the entire environment simultaneously. Every scattered photon, every air molecule, every thermal vibration. You would need to capture all of them, reverse all their interactions, and reassemble the coherence that was distributed among them. This is not practically impossible. It is effectively impossible, in the same sense that unscrambling an egg is impossible. The information is not lost. It is dispersed beyond recovery. This is decoherence. The superposition is not destroyed. It is diluted, spread across so many environmental degrees of freedom that no local observation can ever detect it. The particle looks classical, not because something has happened to it at the quantum level, but because the quantum level has expanded to include the entire environment, and the part you can see, the particle, has been reduced to a state that is, for all practical purposes, indistinguishable from a classical mixture. Let me make this concrete, because the abstraction hides the violence of what is actually happening. Imagine you are running the double-slit experiment. You have an electron source. You have a barrier with two slits. You have a detection screen on the other side. You fire electrons one at a time. Each electron passes through the barrier. If both slits are open and nobody checks which slit the electron went through, you see an interference pattern on the screen. Bands of high and low probability, the signature of a quantum superposition. The electron went through both slits simultaneously. The two paths interfered with each other, and the result is a wave pattern that no classical particle could produce. Now here is the part that most explanations get wrong. They say that if you place a detector at one of the slits, if you check which path the electron took, the interference pattern disappears, and they describe this as observation causing collapse. The act of looking destroyed the superposition. Your knowledge changed the physics. That is not what happened. What happened is that the detector at the slit interacted with the electron. The interaction entangled the detector with the electron. And because the detector is a macroscopic object made of trillions of atoms interacting with an environment of trillions more atoms, the entanglement between the electron and the detector immediately spread into the environment. The detector's atoms jiggled. Photons scattered off the detector's surface. Thermal fluctuations rippled through the detector's material. Each of these processes entangled environmental degrees of freedom with the Which path information. Within 10 to the negative 39 seconds, the information about which slit the electron went through was encoded in the positions and momenta of thousands of air molecules, millions of photons, billions of thermal vibrations. The interference was not destroyed, it was distributed. It is still there, encoded in the correlations between the electron and all those environmental particles. But to recover it, to see the interference pattern again, you would need to capture every one of those environmental particles, reverse every interaction, undo every entanglement, and reassemble the coherence. You would need to unmake the detector, uncollide the air molecules, unscatter the photons. You would need to reverse the thermodynamic arrow of time for a macroscopic object. That is not collapse, that is irreversibility. And there is a vast, crucial difference between the two. Collapse says the superposition is gone. Irreversibility says the superposition is still there, but you can never get it back. Collapse requires new physics. Irreversibility requires only thermodynamics. And Zer's insight, which Zurek formalized and which every subsequent experiment has confirmed, is that irreversibility is enough. You do not need collapse. You do not need new physics. You do not need an observer. You need only an environment with enough degrees of freedom to absorb the quantum information and scatter it beyond recovery. And here is the thing about this insight that should make you angry. It was available in 1970. Zer published it. The math was there. The logic was airtight. And the physics community ignored it for over a decade. Not because it was wrong, because it answered a question they did not want answered. Zer's paper should have been a revolution. It should have launched a decade of research. It should have appeared in textbooks within 5 years. Instead, it was met with something between indifference and contempt. His own doctoral advisor, the nuclear physicist Hans Jensen, who had won the Nobel Prize in 1963, told Zer that the paper was damaging to his reputation. The broader physics community either ignored the result or treated it as the philosophical meandering of someone who should have been doing real physics. The problem was not that Zer was wrong. The mathematics was airtight. The problem was that Zer was answering a question the community had decided was not a question. And the community enforced that decision with the most effective weapon available: professional marginalization. His students at Heidelberg found it harder to get positions. His research program was treated as a dead end. He was right, and he spent the better part of 2 decades paying the price for it. Zer later described this period as the dark ages of decoherence. And in a letter that captures both the bitterness and the vindication, he wrote that, except for Eugene Wigner, nobody seemed to be interested in his suggestion, and so it was just neglected. This changed not until 1981, when Zurek's paper appeared. He added that he was very happy that it had appeared in Physical Review. The unofficial motto of the era was 3 words: shut up and calculate. And here is a detail that matters. That phrase is attributed in nearly every popular science book and YouTube video to Richard Feynman. It was not Feynman. The phrase was coined by N. David Mermin, a physicist at Cornell, and published in Physics Today in April of 1989. Mermin wrote it as a summary of the attitude he had absorbed as a graduate student at Harvard in the 1950s, where his professors told him, and this is a direct quote, that he would never get a PhD if he allowed himself to be distracted by such frivolities. The frivolities in question were questions about what quantum mechanics actually means, about what the math is describing, about the nature of reality itself. Mermin confirmed in a 2004 follow-up article in Physics Today that the phrase was his own, but the misattribution to Feynman persists, because it is more comfortable to imagine that the suppression of foundational questions was the wise counsel of a genius, rather than the institutional pressure of a culture that had decided certain thoughts were not worth thinking. This is the world into which Wojciech Zurek arrived, a world where the deepest question in physics had been declared off limits, where careers had been destroyed for asking it, where the most successful theory in the history of science contained a crack that everyone could see and nobody was allowed to fix. Think about that for a moment. A man had discovered something fundamental about the nature of reality. The physics community buried it for 11 years. And when it was finally acknowledged, it was not because someone went back and read Zay's paper. It was because someone else, younger, better positioned, as a more prestigious institution, published essentially the same insight, with a different mathematical framework and a more careful political instinct about how to present it. That someone was Wojciech Zurek. But to understand what Zurek did and why it went beyond what Zay had done, you need to understand the environment in which Zurek was working. Not the physical environment, the intellectual environment. Zurek arrived at the University of Texas at Austin in 1976. He was 25 years old, freshly out of Krakow with a master's degree in physics. He had come to Texas for one reason: John Archibald Wheeler. Wheeler was 65 in 1976. He had recently moved from Princeton to Texas, bringing with him a reputation that spanned 4 decades of the most consequential physics of the 20th century. He had worked on the Manhattan Project. He had developed the theory of nuclear fission with Niels Bohr. He had coined the term black hole. He had supervised the dissertation of Richard Feynman, and in his later years, he had become increasingly convinced that the deepest questions in physics were not about particles or forces, but about information, about the relationship between the observer and the observed, about the role of measurement in a quantum universe, about whether the universe, at some fundamental level, is made of information. Wheeler ran a seminar at Texas on quantum measurement that became legendary among his students. He asked questions that no other senior physicist would touch. How does the quantum become the classical? What is the role of the observer? Is the past fixed, or does observation retroactively determine what happened? He called this the participatory universe, the idea that the observer is not a passive spectator, but an active participant in the construction of physical reality. And he framed the central question with a phrase that would become his most famous contribution to the language of physics: it from bit. Every it, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence, from yes-no questions, binary choices, bits. Wheeler wrote that phrase in a lecture for the Third International Symposium on Foundations of Quantum Mechanics in Tokyo in 1989. But the ideas behind it had been forming for decades, and the young Polish student who attended his seminar in the late 70s absorbed them at a formative moment. There is a detail about Wheeler that connects the personal to the scientific in a way that matters for this story. Wheeler's younger brother Joe had been killed in combat in Italy in 1944 during World War II. John Wheeler carried the weight of that loss for the rest of his life. Friends and colleagues described it as the defining grief of his existence. And in the late 1970s, Wheeler proposed an experiment called the delayed choice experiment, in which the decision of how to measure a quantum system, made after the system has already traveled through the apparatus, appears to retroactively determine what the system did in the past, whether the photon went through one slit or both, whether it behaved as a particle or a wave. The choice you make now determines what happened then. Wheeler never said this publicly, but his students understood. The man who spent decades asking whether the past is fixed was the man who wanted, more than anything, the past to be changeable. If observation could reach back in time and reshape what had already occurred, then maybe, in some deep sense, the worst things that had already happened could be undone. The physics and the grief were not separate. They never are. Zurek's formal PhD advisor at Texas was William Sheave, but the relationship that shaped his career, that gave him permission to ask the questions the rest of the field had declared off-limits, was with Wheeler. And after completing his PhD in 1979, Zurek stayed at Texas as Wheeler's postdoctoral researcher until 1981. It was during this period that he published the paper that changed everything. The paper, Pointer Basis of Quantum Apparatus, Into What Mixture Does the Wave Packet Collapse, appeared in Physical Review D in September of 1981. Its question is devastatingly precise. And notice how different it is from Zer's framing. Zer had shown that the environment suppresses interference. Zurek asked something further. He asked why, when a quantum system is measured, the result is always expressed in a particular basis. Why does a detector always register a particle at a definite position rather than in some arbitrary superposition of positions? What selects the basis? The answer is the environment, but not in the way you might expect. The environment does not simply wash away the quantum features. It does something much more specific. It monitors the system continuously, interacting with it through forces that depend on particular observables. For macroscopic objects, the dominant environmental interactions are position-dependent. Photons scatter off surfaces. Air molecules collide with them. Gravitational fields pull on them. All of these interactions couple to the position of the object. And because of this coupling, position states are stable against environmental monitoring. A particle at a definite position stays at that position, or near it, even as the environment interacts with it. But a particle in a superposition of positions gets immediately entangled with the environment in a way that destroys the coherence between the position states. The environment selects position. Zurek called these stable states pointer states because they are the states that a measuring device's pointer can actually point to. And he called the process that selects them Einselection, environment-induced superselection. And this was the key insight that Zer's work had missed. Decoherence tells you that interference goes away. Einselection tells you what survives. Decoherence is the death of fragile states. Einselection is the survival of robust ones. After Texas, Zurek moved to Caltech as a Tolman Fellow, and then, in 1984, arrived at Los Alamos National Laboratory as a J. Robert Oppenheimer Fellow. The Oppenheimer Fellowship is one of the most prestigious appointments in American physics, reserved for researchers whose work is expected to define new fields. Zurek was 33. He was carrying two intellectual inheritances: Wheeler's philosophical vision of an information-theoretic universe and Zer's mathematical framework of decoherence. And he was about to synthesize them into something neither of his predecessors could have built alone. Los Alamos suited Zurek in a way that a traditional university might not have. The laboratory has always maintained a culture that tolerates, even encourages, long-term fundamental research alongside its applied mission. Zurek became a laboratory fellow, one of only a few dozen in the theory division. He led the theoretical astrophysics group from 1991 to 1996. He became an external faculty member at the Santa Fe Institute, where he helped found the Complexity, Entropy, and Physics of Information Network, a research program that treated information as a physical quantity, not an abstraction. And he pursued a parallel line of research that, while less famous than decoherence, would earn him recognition across multiple subfields of physics. In the 1980s, Zurek and the British cosmologist Tom Kibble independently developed a theory for how defects, vortices, domain walls, monopoles form during phase transitions when a system is cooled rapidly through a symmetry breaking point. The Kibble-Zurek mechanism, as it is now called, predicts the density of these defects as a function of the cooling rate. It was originally developed for cosmological phase transitions in the early universe, but it has since been confirmed in laboratory systems including superfluid helium, superconductors, Bose-Einstein condensates, and ion crystals. It is one of the few predictions about the early universe that can be tested in a laboratory on Earth. And the reason I am telling you about it is that the Kibble-Zurek mechanism is fundamentally an information theoretic result. It describes what happens when different regions of a system cannot communicate fast enough to agree on a common state. The defects are the boundaries between regions that have independently, without coordinating, chosen different values of the order parameter. They are the scars left by the universe's failure to reach consensus. Keep that word in mind, consensus. It is going to matter. And it was, at Los Alamos, that the idea that had been forming since Wheeler's seminar finally crystallized. But before I tell you about quantum Darwinism itself, I need to tell you about something else Zurek did. Something that is not widely known outside of quantum information theory but is, in its own way, as fundamental as anything in his career. In 1982, 1 year after the Poynter basis paper, Zurek and William Wouters published a paper in Nature. The paper was 3 pages long. It proved what is now called the no-cloning theorem. The no-cloning theorem says that it is impossible to make a perfect copy of an arbitrary, unknown quantum state. You can copy classical information freely. You can photocopy a document. You can duplicate a file. You can replicate a bit. But you cannot copy a qubit. You cannot take an arbitrary quantum state and produce a second system in the same state without disturbing the original. This is not a technological limitation. It is a theorem. It follows directly from the linearity of quantum mechanics, and it has consequences that extend far beyond quantum computing. The consequence that matters for this story is this: if you cannot clone an arbitrary quantum state, then how does the environment make copies? How does the position of a dust grain get recorded 100 million times in the surrounding photons? The answer is that the environment does not copy arbitrary states. It copies pointer states, and pointer states are precisely the states that can be copied, approximately but repeatedly, because their defining property, their robustness against environmental interaction, is the same property that allows the environment to imprint redundant records without disturbing the original. The no-cloning theorem does not forbid the copying of pointer states. It forbids the copying of everything else. And this is why quantum superpositions disappear from the macroscopic world. Not because they are unstable, but because they cannot be copied. They cannot reproduce. They are the infertile species in a Darwinian competition, where fertility, the ability to make copies of yourself in the environment, is the sole criterion of survival. This is the moment when the metaphor snaps into focus. This is the moment when the word Darwinism stops being a literary flourish and becomes a precise physical description. In 2003, Zurek published a review article in Reviews of Modern Physics, volume 75, pages 715 through 775. The article, titled Decoherence, Einselection, and the Quantum Origins of the Classical, is 71 pages long. It is the canonical statement of the decoherence program, and at the end, almost as an afterthought, it introduces the concept that Zurek had been developing for years, the concept that would 2 decades later be confirmed by experiment, Quantum Darwinism. The same year, Zurek published a shorter paper with Harold Olivier and David Poulin in Physical Review Letters. The paper's title tells you everything: objective properties from subjective quantum states, environment as a witness. And the subtitle is the key. The environment is not a bath. It is not noise. It is not the thing you shield your quantum computer from. The environment is a witness. It observes the system, it records the result, and it distributes the record. Here is how it works, in detail that matters. Imagine a single atom. An electron in this atom is in a superposition of spin up and spin down. The atom is surrounded by an environment consisting of, say, 1,000 photons. The electron interacts with each photon through a spin-dependent coupling. After the interaction, each photon carries a tiny amount of information about the electron's spin. Not enough, on its own, to determine whether the spin is up or down. But after the electron has interacted with many photons, each photon carries a partial record, and collectively, a small subset of those photons, say 50 out of 1,000, carries enough information to determine the spin state with high confidence. Now here is the critical point. A second subset of 50 photons, completely disjoint from the first, carries the same information. And a third subset, and a fourth, each independent fragment of the environment, provided it is large enough, contains a complete record of the electron's pointer state. The information has been copied, redundantly, into independent channels. And any observer who intercepts any one of these fragments will get the same answer. Spin up or spin down. The same result, read from different copies by different observers, without any of them needing to interact with the electron itself or with each other. This is objectivity. This is what it means for a property to be objectively real in the framework of quantum Darwinism. Not that it exists independently of observation, whatever that would mean in a quantum universe where everything is entangled with everything else, but that it has been recorded so many times in so many independent channels that any observer who bothers to look will find the same answer. Classical reality is the consensus of the environmental record, and the environmental record is written automatically, continuously, at timescales so fast they are difficult to comprehend. Let me give you a sense of what 100 million redundant copies actually looks like from the perspective of information theory. Think about the position of a single grain of pollen floating in a sunbeam, 1 micrometer across, roughly the wavelength of visible light. Photons from the sun hit this grain at a rate of approximately 10 to the 14th photons per second. Each photon that scatters off the grain carries information about the grain's position. The information is encoded in the photon's angle of deflection, its timing, its polarization. And each of those photons then flies off into the room, into the air, into the walls, into the furniture, into your eyes if you happen to be looking. Each one is a separate, independent witness. Each one carries its own copy of the grain's position. Now think about what it would take to erase that information, to undo the copies, to somehow recapture every scattered photon, reverse its trajectory, and reassemble the quantum coherence that existed before the scattering. You would need to capture every photon in the room. You would need to unscatter them. You would need to reverse every interaction between those photons and the molecules in the air, the atoms in the walls, the electrons in the furniture. You would need to undo the chain of environmental entanglement that propagated outward from the grain at the speed of light. The number of operations required is, conservatively, on the order of 10 to the 26. The number of atoms in the room, and each operation would need to be performed with perfect precision, because a single missed photon, a single uncaptured air molecule, would be enough to preserve a copy of the position information. A single witness left standing would be enough to maintain the consensus. This is why the classical world feels permanent. This is why objects do not shimmer between positions or dissolve into quantum uncertainty in front of your eyes. The redundancy is so overwhelming, the number of copies so vast, the distribution so thorough, that erasing the classical record would require violating the second law of thermodynamics for a macroscopic system, which is to say, it would require a miracle. And miracles do not happen, not because the laws of physics forbid them absolutely, but because the probability is so small that the age of the universe is not long enough for one to occur. And here is a comparison that might help you feel the absurdity of the timescale involved. How fast, for a macroscopic object at room temperature, the decoherence time, the time it takes for environmental interactions to create enough entanglement to suppress all interference and establish pointer states, is on the order of 10 to the negative 39 seconds. I want you to understand how small that number is. The age of the universe is approximately 4 times 10 to the 17 seconds. The Planck time, the smallest meaningful unit of time in physics, is approximately 5 times 10 to the negative 44 seconds. The decoherence time for a macroscopic object is 100,000 times longer than the Planck time, but still 10 to the negative 39 seconds. It is a time interval so short that nothing in your experience, nothing in the history of human civilization, nothing in the entire history of life on Earth provides a useful comparison. By the time the fastest process in the visible universe has occurred, by the time the first photon has been emitted by the first excited atom, the environment has already done its work. The pointer states have been selected. The copies have been made. The consensus has been reached. And you, with your neurons firing at a few hundred hertz, and your conscious processing lag of roughly 300 milliseconds, you are arriving approximately 10 to the 36 seconds late. Let me put that differently. For every second of conscious experience you have, the environment has been deciding what is real for a duration that exceeds the age of the universe by a factor of 1 billion, billion, billion. You are not creating reality by looking at it. You are arriving after the fact and reading the memo. And the memo has a specific shape. Zurek and his collaborators predicted that if you measure the quantum mutual information between a system and increasingly large fragments of its environment, the result should follow a very particular curve. At first, when you are sampling only a tiny piece of the environment, each new fragment tells you something new. The mutual information rises steeply, but then, very quickly, the curve hits a plateau. It levels off at a value equal to the classical information about the pointer state, the entropy of the pointer observable, and it stays flat. You can capture 10% of the environment, 20%, 50%, and you learn nothing new about the pointer state. You already know everything there is to know. Classically, the information has been copied so many times that any small sample is sufficient. The plateau is the redundancy. It is the mathematical fingerprint of quantum Darwinism. And then, at the very end of the curve, when you capture nearly the entire environment, the mutual information jumps again. It rises to approximately twice the classical value. This final jump represents the purely quantum correlations, the entanglement between the system and the full environment, which are by definition non-redundant. They cannot be copied. They exist in the whole, but not in any part. They are the quantum information that the no-cloning theorem forbids from being distributed, and they are the reason that the quantum world, the world of superpositions and entanglement and coherence, remains hidden behind the classical facade. The classical information gets copied and broadcast. The quantum information stays locked in the global state. You can access the classical part from any fragment. You can only access the quantum part from everything at once, and you will never have everything at once. For 15 years after Zurek's 2003 publication, this prediction was just theory, a curve on a graph in a paper. Nobody had the technology to build a quantum system, couple it to a controlled environment, measure the mutual information fragment by fragment, and see if the plateau was really there. Then 3 groups did it in the space of a single year. I told you about these experiments briefly, but they deserve more detail, because the detail is the content. The Rome experiment, published in August of 2018. Mauro Paternostro at Queen's University Belfast and Paolo Mataloni at Sapienza University in Rome built a photonic system using hyperentangled photons. These are photons entangled in multiple degrees of freedom, simultaneously, polarization, and orbital angular momentum and path. They use the polarization of one photon as the system, and the other degrees of freedom distributed across multiple photons in a cluster state as the environment. They then measured the mutual information between the system photon and increasing fractions of the environmental photons, fragment by fragment, one photon at a time. And the curve appeared, the rise, the plateau, the quantum spike at the end, the predicted shape observed in a laboratory for the first time. The China experiment, published in 2019, Jianwei Pan and Chaoyang Lu at the University of Science and Technology of China, the same group that would later demonstrate quantum computational advantage, used a multi-photon quantum simulator with up to 6 photons. They confirmed the saturation curve and showed that the environment efficiently transfers classical information but is inefficient at transferring quantum information. The division between classical and quantum, in other words, is not a line drawn by physicists. It is a feature of the physics itself. The environment broadcasts the classical part and locks away the quantum part, automatically, without any intervention. And the ALM experiment, published in Physical Review Letters in October of 2019, this one was different. This one used a natural quantum system. Fedor Jelezko's group at the University of Ulm in Germany, working directly with Zurek, used a nitrogen vacancy center in diamond. An NV center is a defect in the diamond crystal lattice, a place where a nitrogen atom sits next to a missing carbon atom. The electron spin of this defect is a natural qubit, and the surrounding carbon-13 nuclei, the roughly 1% of carbon atoms in the diamond that have an extra neutron, are a natural environment. They interact with the NV center through magnetic dipole coupling, and the experiment showed that the NV center's spin state was being imprinted naturally, spontaneously, without any engineering, into the surrounding nuclear spins. Quantum Darwinism was not just a feature of carefully constructed laboratory systems. It was happening in a piece of diamond sitting on a lab bench. But these were all small systems. A few photons, a few nuclear spins. The question remained whether the full architecture would hold in a larger system with more environmental qubits and more complex interactions. In April of 2025, that question was answered. A team led by researchers at Zhejiang University, with collaborators at the University of Houston and Los Alamos, published a paper in Science Advances that is, to date, the most comprehensive experimental verification of quantum Darwinism. They used superconducting qubits, the same technology that powers Google and IBM's quantum computers, operating at temperatures near absolute zero. Their system qubit had a coherence time of approximately 130 microseconds. Their 2-qubit gates operated at a fidelity of 99.8%. They coupled the system qubit to an environment of approximately 10 qubits and performed full quantum state tomography on every possible partition of the system environment state. The results were unambiguous. The mutual information plateau appeared exactly where Zurek's theory predicted, at approximately 1.83 bits in their normalized units. Quantum discord, a measure of purely quantum correlations that Zurek himself had introduced in 2001 with Harold Olivier, was zero through the plateau region and spiked only when the entire environment was captured. The branching structure of the quantum state, the pattern predicted by quantum Darwinism, in which the environment splits into independent records, all pointing to the same pointer state, was directly observed in the state tomography data. This was not a proof of concept. This was the full structure. Every prediction Zurek had made, confirmed in a scalable quantum system, published in one of the most respected journals in physics. And it established, with a level of experimental precision that is hard to overstate, that the classical world you live in is a product of environmental selection. And here is the thing that keeps me up at night about these results. They were published, they were covered in physics journals. Researchers in quantum foundations discussed them at conferences, and then the scientific press largely moved on. There was no headline in the New York Times saying, "Scientists confirm that observers are irrelevant to the creation of reality." There was no CNN segment about the most important experimental result in the foundations of physics in a decade. The coverage that existed was measured, cautious, appropriately hedged. The Quantum magazine article from 2019, written by Philip Ball, is excellent. It is also, as far as I can determine, one of the only pieces of serious science journalism that has ever explained quantum Darwinism to a general audience. One article for a result that rewrites the relationship between human consciousness and physical reality. Compare this to the coverage of any result that seems to confirm the specialness of the observer. Any experiment that is even tangentially related to consciousness and quantum mechanics gets front-page treatment. The Wigner's friend experiments performed by Kaslav Brugner's group in Vienna. The consciousness-related interpretations of the delayed choice quantum eraser, any result that can be spun as evidence that the mind shapes reality gets amplified through the media ecosystem with an enthusiasm that borders on desperation. Because the public wants to believe it, because the cultural narrative of the observer as central to quantum mechanics is so deeply embedded that any evidence supporting it is treated as confirmation, and any evidence refuting it is treated as a technicality. Quantum Darwinism is not a technicality. It is the most comprehensive framework for explaining how classical reality emerges from quantum mechanics that has ever been constructed. It has been tested in 4 independent experiments across 3 different physical platforms. It has been endorsed by 2 Nobel Prize winners. It has been published as a definitive book by the world's most prestigious academic press. And it says, unambiguously, that the observer is reading a record that was written before the observer existed. that consciousness plays no role in the creation of classical reality, that the universe was handling the quantum to classical transition for 13.8 billion years before the first neuron fired. And the public has not been told, not because of a conspiracy, because of a deeper, more structural problem. The public does not want to hear it. The media does not want to report it. The physics textbooks do not want to teach it. And the physicists who know it is true, with very few exceptions, do not want to say it out loud. Because saying it out loud means telling people that the most flattering story about consciousness and physics that they have ever heard, the story that their minds create their reality, is wrong. And nobody, not in physics, not in journalism, not in publishing, gets rewarded for telling people that they are less important than they thought. And now I need to tell you about something else. Something that Zurek published in the same year as Quantum Darwinism, 2003, in a separate paper in Physical Review Letters. It has received far less attention than Quantum Darwinism, but it may be even more fundamental. The concept is called invariance, entanglement-assisted invariance, and what it does is something that physicists have been trying and failing to do for 80 years. It derives Bohr's rule. Bohr's rule is the bridge between quantum mechanics and experiment. It is the rule that tells you the probability of each possible measurement outcome. The probability is the square of the amplitude. Amplitude 0.7. Probability 0.49. This rule has been confirmed by every experiment ever conducted. Every prediction quantum mechanics has ever made depends on it. It is the most tested equation in science, and until Zurek, nobody could explain why it is true. Bohm proposed the rule in 1926. He received the Nobel Prize for it in 1954. But the rule was always an axiom, a postulate, something you accept because it works, not because you understand why it works. Multiple physicists attempted to derive it from more basic principles. All of them, in one way or another, assumed what they were trying to prove. They smuggled the conclusion into the premises. The circularity was well known and considered essentially unavoidable. Zurek broke the circularity. He showed that if you have a quantum system entangled with its environment, there are certain transformations you can perform on the environment that leave the system's state unchanged. These are invariance transformations, and from the symmetry of these transformations, from the fact that certain operations on the environment have no effect on the system, Zurek was able to derive the probability rule. Bohr's rule falls out of the structure of entanglement. It is not an axiom. It is a theorem. The randomness of quantum mechanics is not a separate postulate. It is a consequence of the way information is shared between a system and its environment. When you combine invariance with Einselection and Quantum Darwinism, you get something that no other interpretive framework in quantum mechanics can deliver. You get a picture in which the pointer states the probabilities, the objectivity of the classical world, all of it, every feature of the classical world that you take for granted, is derived from quantum mechanics alone. No collapse postulate, no measurement axiom, no Bohm rule assumption, no classical apparatus, no observer, just unitary quantum mechanics and the environment. The classical world is not assumed, it is derived, and that means the observer, the thing that for a century was supposed to be the essential ingredient, the irreducible primitive, the magic spark that turns quantum possibilities into classical facts. That observer was never needed. The derivation goes through without it. The classical world exists, the probabilities are correct, the outcomes are objective, and the observer adds nothing. Zero. The observer is a reader, not an author, a consumer, not a producer, and the entire library was written, catalogued, and distributed before the first reader was born. Now, let me show you what this does to one of the most famous thought experiments in quantum mechanics, because the contrast between the old answer and the new answer is the starkest illustration I can give you of what quantum Darwinism actually changes. The thought experiment is called Wigner's Friend. Eugene Wigner proposed it in 1961, and it goes like this. Wigner's friend is inside a laboratory. The friend measures the spin of a particle. According to Copenhagen, the measurement collapses the wave function. The friend sees a definite result, say spin up. The friend's experience is clear and unambiguous. But Wigner is outside the laboratory. He has not yet looked at the result. From Wigner's perspective, the entire laboratory, including the friend, the particle, the measuring device, everything is in a quantum superposition. The friend has measured spin up and spin down simultaneously, because Wigner has not yet performed a measurement on the whole system. This creates a contradiction. The friend has a definite experience. Wigner says the friend does not yet have a definite experience. Both are using the same theory. Both are applying the rules correctly, and they reach contradictory conclusions. Wigner's resolution was to invoke consciousness. He argued that the friend's conscious experience is what triggers the collapse. Consciousness breaks the superposition. The friend's mind does something that the laboratory equipment cannot. This is where the consciousness causes collapse interpretation comes from, not from experiment, not from the equations, from a thought experiment designed to illustrate a paradox and a resolution proposed by a man who could not see another way out. Quantum Darwinism dissolves the paradox entirely. Here is how. When the friend measures the spin, the measuring device interacts with the particle and then with the environment inside the laboratory, the air, the photons, the thermal fluctuations. Decoherence occurs. Einselection occurs. The pointer state is selected, and quantum Darwinism occurs. The result is copied into the environment, redundantly, millions of times, long before the friend's neurons register the outcome. By the time the friend consciously experiences spin up, the environmental record is already written and distributed throughout the laboratory. When Wigner opens the door and looks at the result, he is not collapsing a superposition. He is intercepting photons that carry copies of the already determined pointer state. The friend's conscious experience is not what triggered the collapse. The environment triggered the decoherence. The environment selected the pointer state. The environment distributed the copies. The friend's consciousness contributed nothing to the process, and neither does Wigner's. Both of them are readers. The text was written before either of them opened the book. And now I need to tell you what all of this means about you, because everything I have said so far has been about physics, about equations and environments and information theory. But the implication of quantum Darwinism reaches past physics, past the laboratory, past the journal papers, into the place where you live, into the structure of your experience, into the question of what you are actually doing when you open your eyes and see a world. For nearly a century, the story of quantum mechanics has been the story of the observer. The Copenhagen interpretation, the version taught in every undergraduate physics course on the planet, places the observer at the center of the theory. The observer collapses the wave function. The observer forces the quantum system to choose. The observer, by the act of measurement, creates definite reality out of quantum possibility. In the most extreme version of this story, proposed by Eugene Wigner in the 1960s and later developed by Henry Stapp and others, it is specifically consciousness that triggers collapse. The conscious mind is the magic ingredient. Without it, the quantum world remains in superposition indefinitely. The moon does not exist unless someone looks at it. Reality waits for an audience. This story is deeply, profoundly, satisfyingly wrong. And the reason it is satisfying is important. The observer-centered story gives you a role. It tells you that your consciousness matters, that your act of looking at the universe has consequences at the most fundamental level of reality. It is flattering. It makes you feel important. And it has been exploited by an entire cottage industry of popular books, TED Talks, and films that use quantum mechanics as a prop for the idea that consciousness creates reality. The secret. What the bleep do we know? 1,000 Instagram posts about manifesting your desires through quantum intention. All of it traces back to a misunderstanding of the Copenhagen interpretation that was already dubious in 1927 and is demonstrably wrong in 2025. The misunderstanding is this. The Copenhagen interpretation says there is a measurement problem. It says the equations do not tell us when collapse happens. It says there is a boundary between quantum and classical that the theory does not derive. And then it says, with a shrug, use the measurement postulate and do not worry about it. That is all Copenhagen says. It does not say consciousness causes collapse. Bohr never said it. Heisenberg never said it. The Copenhagen interpretation is not a theory of consciousness. It is a refusal to theorize about measurement. It says the question is not a physics question. It says, shut up and calculate. The consciousness part was added later by Wigner, by John von Neumann, by a handful of physicists who looked at the gap in the theory and decided that consciousness must fill it. And their reasoning was not crazy. It was wrong, but it was not crazy. The argument goes like this. If the Schrödinger equation is universal, if it applies to everything, then measuring devices are quantum systems too. And measuring devices interacting with particles should produce superpositions of measuring devices, which is exactly what Schrödinger's cat demonstrates. And if measuring devices are in superpositions, then the physicist looking at the measuring device should also be in a superposition. And then the physicist's colleague looking at the physicist should be in a superposition. The chain never breaks. At no point does the Schrödinger equation say, and now collapse happens. The superposition propagates upward through every system that interacts with the previous one, unless something breaks the chain. And the only thing that seems different about a conscious observer compared to a measuring device is consciousness itself. Von Neumann formalized this in his 1932 textbook, Mathematische Grundlagen der Quantenmechanik, where he placed the cut between quantum and classical at the point of conscious observation. Wigner made it explicit in 1961, and the idea, having been written down in textbooks by serious people, took on a life of its own. It migrated from physics into philosophy, into popular culture, into New Age spirituality, losing precision at every step until it became the cultural cliché that your mind creates your reality. Every physicist who has worked on decoherence in the last 40 years knows this is wrong. They know the chain breaks at the environment, not at consciousness. They know decoherence suppresses superpositions long before any conscious mind gets involved. They know the measurement problem is real, but the consciousness solution is not. And most of them continue to teach the Copenhagen interpretation without correction in their undergraduate courses, because the alternative would require spending weeks on decoherence theory. And decoherence theory is not in the standard curriculum, and the standard curriculum is set by committees who last updated it in 1990. And the committees are made up of people who were trained in the shut up and calculate tradition and do not consider the measurement problem to be within the scope of a physics course. This is not malice. It is institutional inertia, but the result is the same as if it were malice. Millions of students are taught a version of quantum mechanics that implies their consciousness matters to physics. And then they go out into the world, carrying that misunderstanding like a virus, spreading it through conversations and books and videos and podcasts, until the misconception becomes so culturally embedded that correcting it feels like attacking people's sense of meaning. You are telling them they are not special. You are telling them the universe does not care about their minds. You are telling them the story they were sold was wrong. Nobody wants to be that person. And so the misconception persists. And here is a misconception I need to correct, because it is the one that pollutes nearly every discussion of quantum mechanics online, and it is the reason this story matters. The misconception is that quantum mechanics proved the observer is special. It did not. The Copenhagen interpretation assumed the observer is special. It assumed a boundary between the quantum and classical worlds. It assumed that measurement is a primitive, an irreducible category that the theory does not need to explain. And when physicists taught this assumption to generations of students, and when those students became science writers and YouTube creators and TED Talk speakers, the assumption calcified into a cultural belief. The observer matters. Consciousness shapes reality. The universe is participatory. Quantum Darwinism does not just challenge this belief. It explains why the belief existed in the first place. The environment makes copies of pointer states and distributes them. By the time you look at something, you are intercepting copies. And because you are intercepting copies, it feels like your observation is what made the property definite. It feels like the act of looking is what forced the electron to choose. But the electron did not choose when you looked. The electron's pointer state was selected and copied a trillion times before the first photon from it reached your retina. Your experience of making the quantum system choose is an artifact of the fact that you are reading the record after it was written. Like watching a movie and believing you are directing it. Like reading a novel and believing you are writing it. Zurek has said this directly in the formulation quoted in interviews and in the promotional materials for his 2025 Cambridge University Press book. Zurek describes the environment as a witness. The photons are the witnesses. The air molecules are the witnesses. The thermal fluctuations are the witnesses. The observer, the human being with the consciousness, and the lab coat and the particle detector is not a witness. The observer is someone who shows up after all the witnesses have already testified and reads the transcript. Alain Aspect, Nobel laureate, endorsed the book by writing that what he values in Zurek's framework is that it does not invoke a magic influence of our brain onto the observed quantum object. Read that carefully. A Nobel Prize-winning physicist is saying in a published endorsement that the previous framework implied a magic influence of our brain onto the quantum world, and that the new framework dispenses with it. But I need to be honest with you about something, because the critics of quantum Darwinism are pointing at a real problem, and ignoring it would be the kind of sanitizing that this channel exists to avoid. Quantum Darwinism explains why all observers agree. It explains objectivity. It explains the classical consensus. It explains why the world looks the way it does to everyone who looks at it. But it does not explain why a particular outcome is the one that gets recorded. It explains the distribution of the newspaper. It does not explain who wrote the headline. Decoherence and Einselection tell you that superpositions of pointer states become undetectable, but they do not eliminate the superposition. After decoherence, the quantum state is still, mathematically, a superposition of all pointer states, each entangled with a different branch of the environment. The cat is still, in the math, in a superposition. The interference between alive and dead is gone, so you will never see a zombie cat. But the question of why you experience alive rather than dead, why this particular branch is the one you find yourself in, that question is not answered by quantum Darwinism. It is not answered by decoherence. It is not answered by any existing interpretation of quantum mechanics. Ruth Kastner, a physicist and philosopher at the University of Maryland, has been one of the most persistent and technically precise critics. Her objection, published in Physics Today in 2015, cuts to the heart of the framework. Zurek's theory starts by dividing the universe into a system and an environment. It then shows how the environment selects pointer states and copies them. But the division itself, the choice of where to draw the line between system and environment, is not derived from the theory. It is put in by hand. And without that division, the framework does not get off the ground. You need to know what the system is before you can ask what the environment does to it. But what counts as a system? Quantum mechanics treats the entire universe as a single quantum state. The decomposition into subsystems is a choice made by the theorist, not a fact derived from the equations. Chris Fields raised a similar objection. The definition of objectivity in quantum Darwinism relies on the idea that different observers can access different fragments of the environment and get the same answer. But what counts as a fragment? How do you carve the environment into pieces? The math does not tell you. You tell the math. And if the carving is a choice you make rather than a fact the theory discovers, then a certain circularity infects the whole program. You need classical notions, the notion of a system, the notion of a fragment, the notion of an observer, in order to derive classicality. The snake eats its tail. Zurek responded in a rebuttal in Physics Today that the system-environment split is not arbitrary, that it is determined by the interaction Hamiltonian, and that decoherence is generic and hard to avoid, meaning the framework is robust against reasonable variations in how you carve up the world. And this is probably right. The physics does constrain the split, but notice what has happened. The split is determined by the physics. The physics is described by the Hamiltonian. The Hamiltonian is defined relative to a particular decomposition of the universe into parts. The circularity is not eliminated. It is displaced. I am telling you this not to undermine the theory. The theory works. The experiments confirm it. The predictions are specific and testable and tested. But the deepest question, the question of why there are systems at all, why the universe admits decomposition into parts, that question remains open. And it is possible, genuinely possible, that this is a question physics cannot answer, that the existence of separable systems is a precondition for the existence of any physics at all, not a derived consequence of any theory. And Zurek has acknowledged, with the kind of intellectual honesty that is rarer than it should be in physics, that a full account of what it means to experience a definite outcome may require something beyond physics. In that 2014 Physics Today piece, he wrote that a full account of collapse involves consciousness and may have to go beyond just mathematics or physics. This is not Zurek endorsing the Wigner position. He is not saying consciousness causes collapse. He is saying something more precise. He is saying that the first-person experience of perceiving a single, definite outcome, the experience you are having right now as you listen to these words, rather than some quantum superposition of other words, may not be a question physics is equipped to answer, that it may belong to a different domain entirely, the domain of the hard problem of consciousness, which is a problem that nobody, not physicists, not philosophers, not neuroscientists, has the faintest idea how to solve. But set the critics aside for a moment, because I need to take you to the place where this story has been heading since the beginning, to the implication that lies at the bottom of everything I have told you. The implication that Zurek has never said explicitly in a paper, but that follows, with logical inevitability, from the framework he built. If the environment determines what is real, and what is real is what gets copied, and what gets copied is determined by the interaction Hamiltonian, and the interaction Hamiltonian is a fact about this particular universe, then classicality is not a feature of physics. It is a feature of this physics, this environment, this set of forces and couplings and energy scales. Position is the pointer observable for macroscopic objects, because the dominant environmental interactions at everyday scales are position-dependent. Photons scatter off surfaces, air molecules bounce off matter, gravity pulls on mass. All of these couple to position, and therefore, the environment selects the position basis. Objects have definite positions. The world is made of things that are somewhere. But this is contingent. It did not have to be this way. And this might be the most vertigo-inducing implication of the entire framework. If the dominant environmental coupling were different, if the physics of this universe selected a different pointer basis, then reality itself would look fundamentally different. Think about what that means. Position is the pointer observable for everyday objects, because the forces that dominate at everyday scales, electromagnetic scattering, thermal contact, gravitational attraction, all depend on position. But imagine a universe where the dominant environmental interaction coupled to momentum instead. In that universe, every object would have a definite velocity but an indefinite position. Your coffee cup would be moving at exactly 3.7 meters per second, but it would not be anywhere in particular. It would be smeared across the room, across the building, across the continent, in a spatial superposition that the environment could not resolve, because the environment's coupling is momentum dependent, not position dependent. And the beings in that universe, made of momentum pointer states, would find this perfectly normal. They would have physics. They would have a version of quantum Darwinism that explains why momentum is always definite. And if one of their theorists proposed that position might be the real pointer observable, the establishment would dismiss it as philosophy. Or imagine a universe where the pointer basis is energy. Every object has a definite energy level, but is in a superposition of positions and momenta simultaneously. A rock in that universe has a precise energy of 3.2 times 10 to the 23 electron volts, but no location and no velocity. It is everywhere and going in every direction at a specific energy. The beings made of energy pointer states would have chemistry of a kind. They would have structures of a kind. And they would look at the universe and see it as obvious and natural and self-evident that reality is organized around energy levels because their environment told them so, because their environment selected for it, because their version of quantum Darwinism wrote a newspaper about energy, and they are reading that newspaper, and it is the only newspaper they have ever seen. The point is not that these alternative universes exist, though in the Everettian reading of quantum Darwinism, versions of them arguably do. The point is that nothing in quantum mechanics privileges the position basis. Nothing in the Schrödinger equation says position is more fundamental than momentum or energy or angular momentum or any other observable. The privilege of position is entirely the result of the environmental coupling. It is the result of the specific way photons and air molecules and gravitational fields happen to interact with matter at the temperatures and densities and energy scales that characterize the surface of this planet. Change the environment and you change the pointer basis. Change the pointer basis and you change reality. The solidity of the floor beneath you is not a fact about physics. It is a fact about this environment. The sharpness of the edges of every object in your visual field is not a fact about matter. It is a fact about how photons happen to scatter off matter at visible wavelengths. The definiteness of position itself, the thing you would have identified before tonight as the most basic and obvious fact about the physical world, is an environmental accident, a Darwinian selection outcome, a copy that got distributed. And once you see this, once you really absorb it, you cannot unsee it. Every time you look at a solid object and feel certain that it is there, at that location, in that shape, you are experiencing the environmental consensus. You are reading a copy, and the certainty you feel, the absolute conviction that the object is real and definite and located precisely where you see it, is not evidence that the object is fundamentally there. It is evidence that the environment has been very, very thorough in its copying. The classical world is not the truth beneath the quantum veil. The classical world is the veil. It is the specific story that this particular environment tells about quantum mechanics. Other environments with different couplings would tell different stories, and all of them would be equally true. And here is where Wheeler's ghost enters the room for the final time, because this is exactly what he meant by it from bit. The it is the classical world. The bit is the information in the environmental record. And the from is quantum Darwinism, the mechanism by which information about selected quantum states proliferates through the environment and becomes accessible to observers. It from bit, not as metaphor, as mechanism. Wheeler proposed it. His student proved it. And the proof changes everything. Wheeler died on April 13th, 2008, at his home in Hightstown, New Jersey. He was 96. In his final years, he had been working on what he called the really big question, the question of how the universe bootstraps itself into existence through acts of observation. He had proposed that the entire universe might be a self-observing loop, a cosmic delayed choice experiment, in which observations made now reach back in time and participate in the creation of the conditions that gave rise to the observers. The participatory universe. It from bit. He did not see the 2019 experiments that confirmed his student's theory. He did not see the 2025 experiment that verified its full structure. He did not see the book his student published that year, 44 years after their collaboration began. And there is an irony in that. The kind of irony that this story keeps producing, connecting the personal to the physical in ways that neither domain can contain on its own. Wheeler spent his career asking whether the past can be changed, whether observation shapes what has already happened, whether the future reaches back and creates the conditions for its own existence. And the answer his student gave him is no. The past is written, the records are made, the copies are distributed, and by the time you observe anything, the observation is already over. Wheeler's question, the question that consumed the last 3 decades of his life, was answered by his own student. And the answer was the one Wheeler feared. The past is not mutable. The records are permanent. The environment wrote them, copied them, distributed them, and nobody, not even a genius asking the most beautiful question in physics, can reach back and change them. In 2024, Zurek was elected to the United States National Academy of Sciences. It took 43 years from his first paper. In 2025, Cambridge University Press published his book Decoherence and Quantum Darwinism, with endorsements from Alain Aspect, Serge Haroche, Charles Bennett, and Maximilian Schlosshauer. Schlosshauer called it the definitive text on the quantum to classical transition. The book is the synthesis of 44 years of work. It runs from Zurek's earliest papers on pointer states through Einselection, invariance, quantum discord, and the full formulation of quantum Darwinism, including the experimental confirmations. It is, in every sense, the capstone, the final statement, the complete theory. 44 years, from the first paper in 1981 to the synthesis in 2025. Zurek waited 11 years for someone to listen. Zurek waited 44 for the experiments to catch up. Everett never saw his ideas vindicated at all. He died in 1982, 3 years too early to see Bell's theorem experimentally confirmed, 4 decades too early to see the decoherence program he inspired bear fruit. Bell himself died in 1990, 1 year before the first clean experimental test of his inequality, 4 years before the first experimental demonstrations of decoherence. The measurement problem moves slowly, not because the physics is slow, but because the physics community is. Serge Harosh, another Nobel laureate, endorsed the book by noting that Zurek proposes a thoughtful reconciliation between Bohr's Copenhagen credo and Everett's many worlds picture. And that line should stop you cold, because what it means is that quantum Darwinism does not choose between the two great rival interpretations of quantum mechanics. It absorbs them both. Copenhagen said there is a classical world and a quantum world, and a boundary between them. Everett said there is only a quantum world, and the classical world is a branch. Zurek says the classical world is the set of states that survived environmental selection and were copied into redundant records. Copenhagen's boundary is the line where the copying becomes so overwhelmingly redundant that the quantum information becomes unrecoverable. Everett's branches are the pointer states, and their environmental records, each branch corresponding to one possible value of the pointer observable, each branch producing its own self-consistent classical world. Zurek did not pick a side. He explained the mechanism that both sides were, in their different ways, pointing at. But the implication that neither side wanted to confront is the one I keep circling back to, the one about you. If you are made of pointer states, and pointer states are the states that survived environmental selection, then you are, in a very precise sense, a product of the same process that produces classical reality. Not in the loose metaphorical sense that you are part of the physical world, in the specific sense that every atom in your body, every molecule, every cell, every neural circuit is a hierarchy of environmental selections. The environment selected position as the pointer basis. Position allowed molecules to have definite shapes. Definite shapes allowed chemistry. Chemistry allowed neurons. Neurons allowed consciousness. You are the end product of a selection chain that starts at the quantum level and runs through 13.8 billion years of environmental filtering. I want to make this visceral, because the abstraction lets you keep the idea at arm's length. And it does not belong at arm's length. It belongs against your skin. The hemoglobin molecule in your red blood cells has a specific three-dimensional shape. That shape is what allows it to bind oxygen. That shape exists because the atoms in the molecule have definite positions relative to each other. Those definite positions exist because position is the pointer observable, because the environment, through electromagnetic coupling, selects for position states and copies them into the surrounding thermal bath, trillions of times per second. The hemoglobin molecule is a pointer state. Its shape is the record of an environmental consensus. And every oxygen molecule it carries is a passenger on a vehicle built by quantum Darwinism. The action potential traveling down your motor neurons right now, the one keeping your eyes focused on this screen, operates through the flow of sodium and potassium ions through protein channels in the cell membrane. The ions have definite positions. The channels have definite conformations. The membrane has a definite voltage. All of these are pointer states. All of them are environmentally selected. All of them are copies, recorded and re-recorded billions of times per second in the thermal environment of your body. The thought you are having right now about whether this is true is carried by those ions through those channels along those membranes. The thought is made of the same stuff as the theory. The skepticism is constructed from the very mechanism it doubts. Every time your heart beats, approximately 60 to 100 times per minute, roughly 100,000 times per day, roughly 3 billion times in your lifetime. It beats because cardiac muscle cells contract in coordination. The contraction is driven by calcium ions flowing through channels gated by voltage. The voltage is a pointer state. The calcium ion's position is a pointer state. The protein conformation of the channel is a pointer state. Your heartbeat is a symphony of environmentally selected quantum states, each one copied into the thermal environment, each one independently verifiable by any fragment of the environment that happens to interact with your chest. The environment knows your heart is beating. It has been recording it in scattered photons and thermal fluctuations since before your first breath, and it will continue recording it after your last. And here is the part that Zurek has not said in a paper, the part that lives in the implication, the part that follows logically from the framework if you do not flinch. If your consciousness is running on pointer states, then your consciousness is a product of environmental selection, not just in the biological sense, not just in the evolutionary sense, in the quantum sense. The states that constitute your awareness are the states that survived interaction with the environment. Other states, other configurations, other possible arrangements of the same atoms that would constitute different experiences, different awarenesses, different versions of you. Those states exist in the equations, but did not survive. They were not copied. They were not distributed. They have no witnesses. You are the consciousness that the environment copied, and all the other consciousnesses, the ones the environment did not copy, the ones that were not robust against thermal fluctuation and electromagnetic scattering and gravitational coupling, those consciousnesses are not theoretical. They are the logical consequence of taking the Schrödinger equation at face value. They are the branches that Everett described, the alternatives that the no-cloning theorem prevented from being distributed, the realities that are real but unreported. And what about the feeling? The feeling you have right now, the feeling that you are the one doing the perceiving, that you are the agent at the center of your experience, making choices, directing attention, deciding what to look at? Quantum Darwinism does not say your experience is an illusion. It says something subtler and in some ways worse. It says your experience is real, completely real, but it is the experience of a reader, not an author. You are genuinely experiencing the world. The colors are real to you. The sounds are real to you. The sensation of sitting in a chair, of breathing air, of existing in a definite place at a definite time, all of it is as real as experience gets. But the content of that experience, the properties you perceive, the values you measure, the outcomes you observe, none of that was determined by your act of perceiving it. All of it was determined by the environment, copied by the environment, distributed by the environment, and made available to you by the environment. Your experience is real. Its cause is not what you think it is. This is the sense in which quantum Darwinism is more unsettling than any other interpretation of quantum mechanics. Many worlds says there are other versions of you in other branches. That is strange, but abstract. Pilot wave theory says particles have definite positions guided by a wave. That is strange but reassuring. Copenhagen says, do not ask about the measurement problem. That is intellectually dishonest but comfortable. Quantum Darwinism says you are a product of the same selection process that produces reality, and you are perceiving that reality through copies that the selection process distributed. And you are experiencing the whole thing through a nervous system that is itself a stack of selected pointer states. And the entire structure is self-consistent and self-contained and has no place in it where you, the conscious agent, are doing anything that the environment did not already do. It takes everything you thought you knew about the relationship between your mind and the world, and it inverts it. The world is not shaped by your mind. Your mind is shaped by the world. And by world, I do not mean the vague philosophical concept. I mean the environment, the photons, the air molecules, the thermal bath, the specific, physical, measurable environment that selects pointer states and copies them. That environment made you. And it made you such that you can only perceive the things it copied. And every step of that chain happened without any observer, without any consciousness, without any act of measurement. The environment did the selecting. The environment did the copying. The environment enforced the consensus. And by the time a conscious mind emerged, billions of years later, the entire classical world was already written, already distributed, already agreed upon by every fragment of the environment. The conscious mind did not create anything. It read the consensus, and it believed, because what choice did it have, that the consensus was the same thing as reality. Zurek asked, in his 2009 Nature Physics paper, how Darwinian is quantum Darwinism? And then he added a sentence that reads like a throwaway, but feels, in hindsight, like the most important sentence in the paper. He wrote that he cannot answer whether quantum Darwinism is in some way behind the familiar natural selection. Whether the informational selection that creates classical reality from quantum possibilities is the same process at a deeper level as the biological selection that created life from chemistry. Whether evolution is not something that happens in reality, but something that reality is. He cannot answer it. Neither can I. But the architecture is suggestive in a way that goes beyond analogy. In quantum Darwinism, the states that survive are the ones that can copy themselves into the environment. In biological evolution, the organisms that survive are the ones that can copy themselves into the next generation. In both cases, the selection pressure comes from the environment. In both cases, the winners are defined by reproductive fitness. In both cases, the losers are not destroyed, but made inaccessible. The extinct species are encoded in the fossil record, but will never walk the earth again. The decoherent quantum branches are encoded in the universal wave function, but will never be observed again. But the parallel runs deeper than survival and reproduction. Think about what mutation means in biology. A random change in the genetic code, an error in copying, a new variant that did not exist before. Now think about what quantum uncertainty means in quantum Darwinism. A random fluctuation in the quantum state, a deviation from the pointer state, a new possibility that the environment will either amplify or suppress. In biology, mutations are the source of variation. In quantum mechanics, quantum fluctuations are the source of variation. In both cases, the variation is random. In both cases, the selection is not. The environment determines what survives. The variation provides the raw material. The selection provides the direction. This is the Darwinian algorithm. And Zurek is suggesting, carefully, with the precision of someone who understands the weight of what he is saying, that this algorithm might not have been invented by biology. It might be a feature of physics. It might be the deepest logic of the universe. And biology might be a special case of something that has been running since the first quantum state interacted with the first environment, 13.8 billion years before Darwin was born. The parallel is not metaphorical. It is structural. And if it holds, if the Darwinian logic runs all the way down, then the emergence of classical reality from quantum mechanics is not a transition from one kind of thing to another. It is the first act of a process that eventually produces you. And here is where I want you to follow the logic one step further than I think anyone has been willing to follow it in print. If the classical world is what survived environmental selection, then what does that make information? In Zurek's framework, information is not something that describes physical systems from outside. Information is what physical systems compete to become. A pointer state is a state that succeeded in imprinting copies of itself onto the environment. That is what a pointer state is. It is a piece of information that reproduced, and the classical world, the world of definite properties and shared facts and objective measurements, is the set of information that won the reproductive competition. The world is not made of matter. It is not made of energy. It is not made of waves or particles or fields. The world is made of information that successfully copied itself into the environment. And you are part of that information. This is Wheeler's it from bit. But Zurek has made it operational. Wheeler said the world is made of information. Zurek showed how. The mechanism is copying. The selection pressure is the interaction Hamiltonian. The reproductive advantage goes to the pointer states. And the result is a classical world that is as real as it needs to be. Meaning, real enough that every independent fragment of the environment confirms the same facts, but not more real than that. Meaning, not real in a way that excludes the quantum alternatives. The alternatives are there. They are exactly as real as the world you see. They simply were not copied. Think about what this means for the concept of existence. In everyday life, you treat existence as binary. A thing either exists or it does not. The chair is there or it is not there. But in quantum Darwinism, existence is not binary. Existence is a matter of degree, and the degree is measured by redundancy. A property exists, in the operational sense, to the extent that it has been imprinted in the environment. A macroscopic object with 100 million redundant copies of its position in the photon environment exists very strongly. A quantum superposition that has not been copied into any environmental record exists very weakly. Not zero. The superposition is still there in the equations, but it has no witnesses, no copies, no records, no fragment of the environment you could intercept that would tell you about it. It exists without being known, and in Zurek's framework, existence without being known is existence without being classical. It is existence in the quantum sense, which is real but unreachable. In March of 2025, Zurek and two collaborators, Akram Tool and Bingtian Yan, posted a paper on Arxiv that takes this logic to its mathematical conclusion. The paper is titled Consensus About Classical Reality in a Quantum Universe, and it proves, as a theorem, that any two observers who access sufficient fragments of the environment will always agree on the pointer state of the system. Always. Not approximately. Not in the limit of large environments. Exactly. Within the framework of quantum Darwinism, classical objectivity is a mathematical necessity, but a theorem about consensus is not a theorem about completeness. Consensus means all observers agree. It does not mean that what they agree on is all there is. And this is the thing I keep coming back to. This is the thing that sits at the center of quantum Darwinism, like a weight that the framework was built to carry but was never designed to explain. The classical world is the consensus. The consensus is enforced by redundancy. The redundancy is created by the environment copying pointer states and distributing the copies. And the things that are not in the consensus, the things that were not copied, the quantum states that did not survive the Darwinian competition, those things are not fiction. They are not approximation. They are not error. They are the parts of reality that the environment chose not to report. And the environment's choice, if you can call it that, was not arbitrary. It was determined by the physics, by the interaction Hamiltonian, by the specific way matter and energy and fields happen to couple in this universe. But it was a choice in the Darwinian sense, a filtering, a selection. And a selection implies that something was selected against. The measurement problem started as a question about where to draw the line between quantum and classical. Quantum Darwinism answers that question. The line is drawn by the environment. The line is wherever the redundancy becomes sufficient for consensus. The line is not sharp, because redundancy is a matter of degree, but it is definite enough for every practical purpose. Objects with 100 million copies of their position in the environment are on the classical side. Quantum superpositions with no copies are on the quantum side. And the transition between them, the crossover, the place where Schrödinger's cat becomes either alive or dead, rather than both, is determined by the rate at which the environment makes copies of the pointer state. For a cat-sized object at room temperature, that rate is approximately 10 to the negative 39 seconds, which is why you have never seen a cat in a superposition. The environment prints the newspaper too fast for you to catch the press still running. But the measurement problem was never just about where to draw the line. It was about what happens to the things on the quantum side, about the states that were not selected, about the superpositions that leaked away into environmental entanglement, about the branches that Everett said were real, but that nobody could see. Quantum Darwinism does not make those branches disappear. It explains why you cannot access them. It explains why the classical world feels absolute and singular. It explains the lock on the door, but it does not tell you the room behind the door is empty. And this is the thought I want you to take with you, because it is the thought that Zurek's framework forces on you, whether you want it or not. The classical world is not all there is. The classical world is a curated exhibit, a selected highlight reel, a consensus document produced by environmental witnesses and distributed to environmental readers. And everything else, the quantum everything, the superpositions, the entanglements, the coherences, the vast unmapped territory of Hilbert space that the no-cloning theorem prevents from being copied, and the environment prevents from being witnessed. All of that is still there, still real, still carrying the full mathematical weight of the Schrödinger equation, and still completely, permanently, structurally invisible to you. Not because you are looking in the wrong direction, not because your instruments are insufficient, but because you are made of the selected states. Your eyes are made of pointer states. Your brain is made of pointer states. Your consciousness, whatever it is, runs on pointer states. You are the product of the selection, and a product of selection cannot perceive what the selection excluded. You would need to step outside the consensus to see what was left out. And there is no outside. There is no place to stand that is not made of the states that survived. There is no observation you can make that is not the reading of a copy that the environment already distributed. Wheeler wanted to know how the quantum becomes the classical. His student showed him the quantum does not become the classical. The classical is what the environment copies. Everything else remains quantum. And you, who are made of copies, can only see copies. You are a mirror, looking at mirrors, all reflecting the same selected image, all confirming the same consensus, all unaware that the room is full of things the mirrors cannot reflect. The calculations are finished. The experiments are done. The results sit in physical review letters and science advances, and a Cambridge University press book, with endorsements from 2 Nobel laureates. And what they say, plainly, is that you were never the point. The environment was the point. The information was the point. The selection was the point. And the observer, the you that feels so central, so necessary, so irreplaceable in the act of perceiving reality, is the last thing the process produced, and the first thing it does not require. The copies were distributed before you opened your eyes. The consensus was reached before you were born. The pointer states were selected before the first cell divided. And the reality you experience, the one solid, undeniable world you have lived in every day of your life, is not the universe. It is what survived. The rest is still there, still real, still present in the equations, still carrying the same ontological weight as the chair beneath you and the screen in front of you. You just cannot reach it. Not because you are not looking hard enough, not because your instruments are not sensitive enough, but because looking is reading, and the environment only publishes one edition.